Yeah?
Just noticing that the boiling point and freezing point are pretty different. It's also I saw somewhere where the freezing point and boiling point elevation with ions. That can get.
Well, yeah. That's what this is for. This is for.
Oh, but the freezing point doesn't happen?
No, they just didn't put it up there. Because we're going to talk about it separately next.
Okay, so is there supposed to be the eye?
We're going to talk about it separately next. So, this kind of started to come up on Monday. Today's Wednesday. So we're talking about colligative properties. Colligative properties, basically, we talked about all this stuff, okay, not osmosis, but we talked about freezing point, boiling point, vapor pressure, all of that stuff we talked about in chapter 12, and how it is, the property is determined based on intermolecular forces, right? So we talked about how intermolecular forces affect vapor pressure, freezing point, and boiling point, right? So that's for a pure substance. What we're talking about in this section is, how are these things affected if I have a solution? And so it turns out that if I have a solution, the vapor pressure is lower, the freezing point is lower, the boiling point is higher. And so everything on the board here summarizes all of that, and everything on the board is also in your book. So you need to know, of course, the effect of the solute on these properties. But the thing I want to spend more time on talking about this morning, before we get to some questions, is the identity of what's in the solution and what happens when we put it in the solution. So, colligative properties are dependent upon the number of particles in the solution, not the identity. Now, of course, the number of particles is determined by its identity, but the properties are not changing based on it being this compound versus this compound. They're changing based on how many ions do I have versus, here versus over here. It doesn't matter what the ions are, it's just how many are there. So what this requires of you is you need to be able to identify if something is a non-electrolyte, a weak electrolyte, or a strong electrolyte. And when did you learn how to do that? In Chem 101. You still need to know how to do that. So you need to be able to look at a compound and identify it as non-weak or strong electrolyte. Because when we're making these solutions in water, we're just going to talk about water right now, you need to be able to say, okay, when I put this in water, what does it do? And that is going to determine this number of particles that's so important. And so it all starts with you being able to identify what happens in the water. Okay, and then you have to remember that it's the number of particles. Okay, because that's the most common mistake in all this colligative property stuff, is people forget this right here. And they'll do the entire calculation correctly, except that they forget about it being the number of particles. Okay, and that's a crappy reason to miss the question. So, let's talk about it. So, in Chem 101, we talked about this kind of situation, right? So I take my sodium chloride and I put it in water and it dissociates and I get sodium ions and I get chloride ions. Okay. If I were to ask you, if I take 1 mole of sodium chloride and I dissolve it in water, how many moles of ions do I get? And that would make me happy because you remembered. Okay? And that's what we learned how to do in Chem 101. And I'm glad you remember that. Okay, now I'm going to tell you what really happens. I lied to you. We don't really get 2 moles of ions. It's close. So I taught you that the ion gets surrounded by water molecules by that hydration shell and they cannot get back together. Guess what? They can. Okay, so to a small extent, the cations and the anions can get back together. And so what that means is, instead of being 2, it's really less than 2. Okay? A little bit. So when we're talking about these colligative properties, there's what we do on paper, which in this case would be 2 moles of ions. And there's what happens for real, which is less than that. And so in some of these up here, we see this I. Okay, and there should be one here too. We see this I in the equation. Now your book talks about all the properties and then they bring up I. I think it should be the other way. I think we should just talk about it all from the get-go. So we need to figure out where this I value comes from. So this I is the Van Hoff factor. Okay? And so you need to be able to figure out what it is. So your book puts it into a relationship of the number of actual particles in the solution over the number of formula units. Now, I have a question for you. It's not on the slides, so you have to listen. How do we figure out the number of formula units? We look on the left side of the arrow, that's answer choice A, or the right side of the arrow, that's answer choice B. How do you figure out how many formula units? Left side of the arrow A, right side of the arrow B. Quick, fast. This is not really a big point of discussion. A or B? Number of formula units. Left side or right side of the arrow? Last call.
So I think it's which one is it? Straight from.
So I'll remind you that the number of formula units is an ionic compound's equivalent to a molecule in a covalent compound. So covalent compounds, we talk about individual molecules. Ionic compounds, we talk about formula units. So I can have 1 formula unit of sodium chloride, or 2, or 3, or whatever. Okay, so this here is the number of formula units. Okay, so that's the relationship that we are going to look at to determine this numerical value of I. So if you had a non-electrolyte, I would be 1, because you'd have 1 particle and 1 unit, right? There's just one thing and it does one thing. It just sits there, okay? So in sodium chloride, for example, the actual number of particles we expect to be 2. And that's where you come up with this 2, right? But it's actually a little bit less than 2. The number of formula units being 1. And so we come up with this number that's like 1.97. And so we're going to have numbers that are very close to what we learned how to do in Chem 101, but they're going to be a little bit smaller. Okay? Now, there's another way to calculate this, because we can't just walk up to the solution and ask it, how many particles are in you? That doesn't work. We need to do things experimentally. So experimentally, what we're going to do is we're going to experimentally determine the value of a colligative property. Okay, whether it be the freezing point, depression, or the boiling point elevation, it doesn't matter. Some measured colligative property. we're going to divide that by the value of that colligative property that we would calculate if it were a non-electrolyte. And so we're coming up with a ratio of what's going on for real and what would we have if it didn't ionize or dissociate. And that's what's going to give us this value for I. And so we're going to think about this conceptually because you're going to see a lot of different presentations of determining the Van Hoff factor. So now, if I don't give you the Van Hoff factor, what do? What do you use? So if I wanted you to calculate the freezing point of a solution of potassium sulfate, and I did not give you the value for I, what value would you use for I? Potassium sulfate. What value would you use for I if I asked you to calculate the freezing point? Or the boiling point, or I don't care, pick one, it doesn't matter. What do you think? I want somebody that I've never heard from to raise their hand down. That I've never, ever heard from. Three. Why? Because there's 3 ions in the potassium sulfate. And we know that it's not really 3. But if I didn't give it to you, we also know that it's pretty close to 3. So we can't use 1. Because we know it's not 1. So if I don't give you the Van Hoff factor, you need to use the Chem 101 expected value. We'll call it that. Okay? Do you have any questions about anything up there or anything we just talked about down here?
You said there's supposed to be an ion osmosis. Where is it?
It's invisible. Don't you see it?
So if the I value is always going to be less than 3, just take it. What's the actual value?
So the question is, if the I value is going to be less than 3, then what is the actual value? Well, the thing is, it's dependent on concentration. So it's dependent on the identity of the ionic compound and the concentration of the ionic compound. So we could go look it up, okay? And I might give it to you. But if I don't, I want you to just calculate it as if there was 100% dissociation and no ion recombining, so that I know that you know it's the particles that matter. Does that make sense? Because I need to know that you recognize the fact that it's the number of particles that are important in these colligative properties. Because if you use an I value of 1, what that tells me is well, okay, one of 2 things. You didn't know that it dissociated, or you just forgot about the whole point of colligative properties.
Dr. Carpenter, under freezing point up there, solution freezes at lower temperature than, I think it says impure solvent. That's supposed to say then a pure solvent.
Yeah, you guys are awfully critical.
Sorry, I was just the improper. Thank you.
I'm going to tell them how critical you are of their notes. We won't do this again. Next time we're going to just let you do it.
That's what you're looking at.
So the question is, if you have a weak acid or a weak base that doesn't ionize completely, but we know it ionizes, what do? Same kind of thing. So if I had, give me a weak acid. Good for you for remembering that's a weak acid. If I have HF, next week. Okay, so we know that I is not 1. We also know that I is not 2. Right? Somewhere in between. I would really, really need to give you that value. Okay? Because the percent ionization varies greatly for weak acids. So it's not like the sodium chloride and all the ionic compounds where the Van Hoff factor is going to be very close to that whole number that we predict. Weak acids, that's not necessarily going to be the case because we draw this equilibrium arrow, okay? But sometimes this equilibrium arrow is like this, but sometimes it's like this, okay? Sometimes we have way more on this side than we do on this side. Sometimes we have way more on this side than we do on this side, okay? It's called the percent ionization. We're going to do it in like 3 chapters from now. So I would really need to give you that. What else?
Does it depend on the solvent? Which solvent is the HF?
Well, we're just going to talk about water as a solvent because it's the easiest thing to talk about. Especially because when we're talking about acids, the only way it's an acid is if it's in water. Because the ionization is the reaction of the molecule with the water, and that's what makes it the acid. Again, we'll do that in about 3 chapters. What else? Okay, well, then you can answer questions for me.
Some kind of order.
Well, I can tell by the name, it's like some sort of there's a carbon chain. Exactly. It's like something working and it's
So do you remember the very first thing I wrote up here? The number of particles. It's the number of particles. So yes, 3 is the biggest number up there. But if I put 1 mole of cobalt nitrate into solution, I'm going to get 3 ions. If I put 3 moles of ethylene glycol into solution, I'm going to get 3 moles of particles. But if I put 2 moles of potassium chloride in solution, I'm going to get 4 moles of particles. Because each mole gives me 2 particles. 2 times 2 is 4. So you A, need to remember that it's the number of particles that's important. And B, need to see where these particles are coming from. And again, that goes back to Chem 101. Alrighty? Do this.
Oh wait. So the higher the pressure, the more likely it'll fall together. What's the chemical formula for polish drying?
Doesn't matter.
Do you need it?
You get 50 grams per mold.
I mean, do you need the formula?
If you sell there's a hydrogen bomb.
Well, that will matter. Question is, does it form ions or not? You think so? Oh, wow. So, which one has the greatest osmotic pressure? A, B, C, or D? Which one? I can't tell what you're saying.
Everyone's saying something different.
I know. I think everybody is saying something different. Someone that, again, I've never ever heard from, raise your hand and tell me which one is going to have the greatest osmotic pressure. That I've never heard from. All right. Which one's next? Somebody raise your hand. That I've never heard from. I've got 22 minutes to wait. And I will. I could randomly pick someone, and that's what's going to happen next. Someone I never heard from. Raise your hand. Now, is it right?
Oh, that.
I took your answers. I never said if they're right. Are they right? So let's talk about it. So what do we care about? The number of particles, right? So let's talk about what's happening in these. What kind of compound is A? In terms of electricity. So non-electrolyte, B? It's a weak electrolyte, C? It's a strong electrolyte, and D? It's a non-electrolyte. So if I'm thinking about A, I is what? I is 1. If I'm thinking about B, I is what? It's greater than 1, right?
Yeah.
It's between 1 and 2, but we know it's greater than 1. And what about for C? Pretty close to 2. And what about D? Is 1. Okay, so looking at these, that seems pretty good, right? Because I got 2. That seems pretty good, because we know it's greater than 1. So now the question is, between these two, because they both have an I of 1, right? So now we're thinking about the number of particles in these solutions. Well, here, if we had, say, 100 milliliters of solution, and we had 0.1 moles, right? Or 0.01 moles. If we think about this polystyrene, it's huge. It's a humongous molecule. We would need 350 grams to get to the place where we'd match the concentration up here in 100 milliliters of solution. Do we have 350 grams? No. And that's why I didn't want you to use a calculator, because you didn't need to. If you recognized, first of all of this, okay, and then just used a little bit of common sense. This is a gigantic molecule. We would need so much of it to get to this concentration. And we only have 1 gram. The concentration is really, 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 really low. And so, yes, A will be greater than D.
How does temperature play a role? Because osmosis does take that into account, and one of them has a different temperature.
Oh, right. So the question is about temperature. So the second one is at a little bit higher temperature. So what do you think about that?
Is it measured in Kelvin, so it's small amount of yes, there's size. Okay, so it's not going to be as big of a change as the eyes.
Right. So basically, the effect of the temperature is going to be much smaller than the effect of the I value. Okay? Go ahead.
For letter B, you said I is greater than 1. Is that because of the hydroxide there, or is that because it's just...
Because this is an acid.
Right.
And so we know it's going to ionize at least a little bit, because it is an acid.
Is that a Bronsted base, though? Even though it's what kind of Bronsted is that?
And Bronsted acid. Because it's an acid. It's gonna donate a proton.
Right.
Other questions? Alrighty.
So it's 2 moles times 0.1. 3 times 0.0, not about 3 Yes, but you'll
So we're going to do the same kind of analysis here. What we care about is the concentration of particles. So what's the concentration of particles in the calcium chloride? Really? And how about in the sodium chloride? HCl. And acetic acid. Are you just guessing, or did you calculate it?
Well, since it's a weak electrolyte, it has to be between 0.1 and 0.05.
Since it's a weak electrolyte, it has to be between 0.05 and 0.1. So where'd 0.07 come from? You just made that up. I bet you're wrong. Because I don't think you calculated it. Because you don't know how yet. Because we're going to do that in about 3 chapters from now. Alright, how about this one? 0.1, because it's a non-electrolyte. So, once you do this, you just got to put them in order. Right? 0.3, 0.2, 0.15, 0.1, and somewhere in there. But again, you have to remember that what we care about is the concentration of particles, and you have to be able to come up with the concentration of particles. That I will again remind you, you learned how to do in Chem 101. Questions? Well, we didn't calculate the freezing point. We didn't have to. No, we're just predicting which of these would have the greatest effect on the freezing point of water. So the freezing point of water is 0, but the freezing point for all of these solutions is not going to be 0. And they're going to change based on whatever this is. We used Chem 101. Huh? We changed these concentrations into concentrations of particles, just like we learned how to do in Chem 101. I'm not going to write it out on the board. Other questions? You mean the concentrations over here? These concentrations over here are determined by the identity of the solute. Is that what you're asking me? Yes. That's right.
Okay, so for HC2, H3O2, there are 6 ions?
No. There's somewhere between 1 and 2 ions. We don't know how many ions. It's more than 1, less than 2.
Is that the same thing for C2, H3O11?
No, because that is a non-electrolyte, so there's just one molecule. HC2H3O2 is what compound?
Sugar.
HC2H3O2, what is that? That's acetic acid. You have to be able to recognize these formulas, guys.
For Van Hoff factors, it was defined as number of particles under dissociation over number of formulae units dissolved. So wouldn't that be, for example, if you had like 1.15 molality sodium chloride, wouldn't that be 2 over 0.15? Because of this over the number of formula units additionally dissolved.
Well, you're trying to apply molality to that formula and get to that. Like they're talking about actual number of particles. Yeah. Good? Yes?
Yeah. Okay, so what you were saying is that how much one ion?
Right. Well, they have no ion. They don't do anything. They're just one thing. One particle.
Okay, and ionic compounds have two ions?
Well, it depends on the ionic compound.
Alright, and strong electrolytes have, they always have slightly less than two?
No, it depends on the identity. You need to go back to chapter help me out. 2? I mean, when did we learn that?
I don't know.
I don't know. I'll get somebody's book and find out what chapter it is for you. Come up with a plan, and I'll give you the numbers. So now, tell me how you calculated it. Because I'm curious to know what your approach was. Got it. To solve for what?
For I.
But what did you get? Molarity.
First we divided the grams for the molar mass. So it's 0.441 grams divided by 111.1, and we found the moles. And yeah,
Right, but that's not the actual molarity.
that's the number of moles, but then we divided by the liters.
Right. You do that for the ions or for the compounds?
I was supposed to do that.
Well, that's the third way to solve this problem. Good job. So I did it a completely different way, and the last guys, they did it a completely different way. This is fascinating to me. It just goes to show you, again, that there's more than one way to solve most of these problems. So, there are many problems that we didn't get to. I'm going to put them all on Blackboard. I suggest you do them. I will highlight the correct answers in red. But you should make sure you get the correct answers. In addition to doing all of your end of chapter stuff. See you